This afternoon, Professor Fresse he will talk about towards higher dimensional analog of the tools of Drinfeld associators.
Okay, thank you very much for the invitation. So I would like to start with this talk with very short recollections about the definition of Drinfeld associators. So very basically, this set, which I will denote by S of K, so K is any field, it's a characteristic zero field. This set can basically be defined as a set of power series on two variables, T1, 2 and T2, 3. So power series means element in the completion of a free algebra generated by this T1, 2 and T2, 3, satisfying some equations, satisfying a unit equation, a pentagon equation, and some hexagon equations. And in Drinfeld's paper, it's explained how to relate the construction of such power series to some kind of braided monoidal category construction. So I would like to formalize this process in terms of operads. So in 1 minute I will explain that this Drinfeld construction is actually related to an iso between this set and some set of operad isomorphism from an object which I will denote by PAB hat. This is the Maltsev completion, so the hat refers to the Maltsev completion process. So this is the Maltsev completion of an operad of parenthesized braids. The second object is another operad, which I will denote by CD hat. This is the operad of chord diagrams. So basically, both of them are operads in the category of categories. And chord diagram is a collection of groupoids of categories, which are actually groups. You have only one object, and the morphisms in this group, the morphisms in these groupoids are formal exponentials of an object which I will denote by PR. So this is the Lie algebra of infinitesimal braids on R strands. So this object was denoted by TR, if I remember well, in Alexeyev Stork. So it's also called the Drinfeld-Kono Lie algebra. So the fact, to explain some ideas, the fact, ideas rather, so the idea is that CD hat, this operad acts on the representations, the category of representations, any Lie algebra equipped with an R matrix. And the operad structure encodes some kind of universal operations governing this governing some structure associated with this category. Operations associated with this structure, with a structure of such a category. R matrix means matrix in G, tensor G satisfying the usual commutation and Young-Baxter equation. Okay?
Sorry. I might be confused, but do you really need an R matrix? It's not enough to have an invariant.
Yeah, okay. Okay, so just to give the idea. Okay. Yeah. No, just, yeah. And so the points of PAB, so it's an operand governing a multiplicative structure, so some tensor covering braided monoidal categories with strict units. The existence or giving an ISO, such an ISO from PAB. So this giving such an ISO provides a process to produce a braided monoidal category structure from such an R matrix. Okay. Provides a process. Symmetric, braided, sorry, monoidal category structure. From an action of this operand CD hat. So basically this is what is explained in Drinfeld's paper. This was one motivation of Drinfeld. Okay. And so I would like to explain some kind of generalization of this picture which arises from the configuration of little disk operand. So I would like to start with the following statement. So this is actually a theorem. So my goal is to explain this result and to explain how this leads to higher dimensional generalization of this PAV and CD. Okay. So briefly, so D2 is the operand of little 2 disks. So this can be regarded as a topological counterpart of this operand PAV. And topological counterpart means that if you take the classifying space construction, so this operand basically consists of groupoids. You can form the classifying spaces associated to these groupoids. Then you get an operand which is equivalent to this object. Okay. And this object is the cohomology. So this is an operand in spaces. Here I'm considering the cohomology of this operand. So I get a structure, and I apply some kind of derived functor construction to go back from graded objects to topological spaces. So it's a functor. So it's a construction which takes some kind of operand in graded commutative algebras, and the output is an operand in topological spaces. Okay. And so I would like to explain that this object is related to this curve diagram of Rad, and the connection is given by this the algebra of infinitesimal braids. I mean, so basically, one takes exponential of elements in this basically algebras to get this groupoid, and here the connection is given by some kind of Koszul duality process. And so here I'm considering this iso, so I forgot to say here that the set of Drinfeld associators you have, so it depends on a parameter mu which is in K. Okay, so there are some yeah. And throughout this talk I will consider the special case where mu is 1. Okay, so this is the special value that this one refers. So I will explain very quickly later on what. So there is some kind of topological counterpart of this condition, which I will explain later on. And there, this notation stands for the homotopy category of topological operators, the rational homotopy category of topological operators. So this is the topological objects. I will not really give an exact definition. So the maps here are maps of topological spaces, basically. And homotopy category means I consider a quotient of a set of topological maps by some kind of homotopy relation.
Your symbol lambda is an intersection.
Oh, lambda refers to the unit structures, to the unitary operations. So it refers to the fact that here I'm considering braided monoidal categories with a strict unit. So it refers to the preservation of unit conditions. And I'm not going to insist on this lambda. Unit preservation. So there is something similar on the topological side, but I'm not going to be very explicit on this one. So it's a technical point. Yeah, but it's actually crucial.
So I can see what is 1? This is 1.
1. So you have this.
Mu equal 1.
Mu will be equal to 1.
When the mu equals 0, then this is the automorphism CD and the automorphism.
Yeah, so maybe, so yeah, mu equals 0, you get a GRT, okay? And this is related to some kind of self-homotopy equivalence of D2. Okay. So the main purpose of this talk is to explain this statement and how this leads to, so for higher dimensional versions, we would like to take, so this is an approximate of little disk of dimension 2. And what I would like to explain how this picture becomes when we take little disk of dimension n larger or equal than 2. And so I've divided my talk in 3 parts. So I will give some brief recollection of the little disk pictures and explain in basic terms the connection with multiplicative structures and categories, which include braided modular categories. In the second step, I will explain I will come back to the definition of SVA algebras and explain how to get higher dimensional versions of SVA algebras and how they relate to the cohomology of Dn. So I mean to explain this correspondence for all of them. And then at the end I will explain the definition of this object and explain how to compute, to get a computation method like this for this mapping space. Okay, so let's start. So DNR, I should recall, this is the space of configurations of R little n disk C1 up to CR inside a fixed unit disk. So we denote this disk as Dn. configurations means that, so I give an example. For instance, this is a picture of an element in D2, 3. Okay. So configuration means that these disks have the disjoint interior. So if you forget the radius, or rather if you shrunk this to points, then you get the space of configurations of R points in Dn. Okay, in the interior of Dn. Okay. So this space is equivalent to the space, so this is actually a homotopy equivalence. So this means if you look at the topology only, you get a space that is homotopy equivalent to the space of configurations of R points in Rn. That you have more, and in this space you have some kind of a quadratic composition. So the spaces are kept with a quadratic structure. So this means basically, if you take another configuration of disk, and this one, then you can plug this second composition to one little disk of this configuration to get another object. Okay. So, and in a sense, this operation which reflects some kind of composition of operation in this algebraic picture. Okay. So. I'm not going to give more details on this subject, so on this structure. So I will just use very basic intuition on this object, on this notion. So first statement, you have a Freund theorem. If you take the classifying space, the fundamental groupoid of this space, then you get braids, okay? And you get actually something. You get so it's an operating groupoid. You get an operating groupoid which is equivalent to this oprat, which I have denoted by PAD. Okay. So it's this parameterized braid. So this means that so it's. I'm not going to explain this identity in details. So just say it's something which should be intuitive. So you consider the fundamental groupoids are homotopy classes of paths in this space. And you see very geometrically. So for instance, that to such a homotopy class of paths, you can associate a geometrical braid. Okay. So for instance, this one. So you take the homotopy class of this path, so it's a path in this space of configuration of three little disks, and you just forget the radius, and you get a braid. Okay. Different geometrical braid in the unit disk. So this is the picture of a path from 0, of the positions of the disk in the path from 0 to 1. Okay. So I'm not going to insist on this topological definition. So you know that braids, so you can define braid groups either geometrically by isotopy classes of braids or algebraically. Okay, so this is, so in that case I'm considering the geometrical picture, so it's something which is closely related to the geometrical picture, this operad, but you have also an algebraic definition of this operad. foreign type. So it's an upright in groupoids. So this means that it's a collection of components, P, A, B, R, which are groupoids. And the object, so I should say that the object is an upright in group. So you have to consider to look at objects and morphisms. And the object is a free upright with one generating operation, with one generator. Which I will denote by x1 tensor x2. So it lies in PAB2. So it represents some kind of abstract operation on two variables. And free upright generated by this element means that the objects, the half component of this upright, are words, or parenthesized words, representing on R variables x1, xr, representing formal composites of this generating operation. X1 tensor x2. For instance, in the case R equals 3, then you get this word x1 tensor xj tensor xk with this parenthesization, or this one xi tensor xj tensor xk. And here ijk runs over commutations of sigma 3. So the words, so each variable x1 up to x3 is supposed to occur only once in such a world. And the morphisms is generated by the morphism of Rad, in some sense, is generated by an associator, which is a morphism going from x1 tensor x2 tensor x3 to x1 tensor x2 tensor x3 and 2. Okay, so that's an associativity ISO, an associator, and a bracket. You have to assume that this morphism satisfies the usual constraints associated with braided symmetric monoidal category. Usual unit, pentagon, and hexagon relations of braided monoidal categories. So generated by these morphisms, that to get all morphisms of this upright, you consider upright composites. This means that you can plug such a morphism inside a word of x1, xr, okay, either alpha or tau, or you can also consider categorical composites of these morphisms. Okay, so use both upright So paradigm means the substitution of a variable by an iso. In categorical composition of variables. So I would like to get a higher dimensional version of this opera, okay, of this algebraic structure. So in the higher dimensional case, so the fundamental group point doesn't make sense because the operas Dn for n larger than 2 are simply connected, so you don't have any fundamental group. But the points that this equivalence is equivalent to the fact that D2. So you have this fundamental groupoid functors, which goes from topological spaces to groupoids, and the classifying space is the functor going in the converse direction. Okay, and for spaces which have only fundamental groups, no homotopy in higher dimension, this result implies that the space D2, for instance, this one, is homotopy equivalent or is weakly equivalent to the classifying space of a groupoid. Okay, so this B is the classifying space construction. Okay, so this equivalence is classical for spaces, and it really extends to operas in topological spaces. I mean, to spaces equipped with such multiplicative structures. So in higher dimension, what you have is the following result. It's a statement, it's a theorem by it's a theorem by four authors, which are Baltenau, Fedorovich, Drinfeld, and Prof, which says that Dn is equivalent to the classifying space of another opera, which I will denote by Mn. So this is the opera governing n-fold monoidal categories. So it's n-fold monoidal categories are just categories C equipped with n tensor products operations tensor 1, tensor 2, tensor n, satisfying some kind of distribution relation. So this means that you have so for each pair ij, so you can form the word x1 tensor over I of x2, tensor over j of x3, tensor over I of x4. And it is assumed that you have a morphism going to this composite of tensor product to a composite where you switch the role of the tensor of I and j. I mean, you first form xi tensor x3, and then x2 tensor x4. And braid monoidal categories categories in the direction of this subpart are the same thing as categories. There's two-fold monoidal categories, such that the first tensor product is equal to the second one, and this distribution morphism is an iso. Summarize, to get a higher dimensional version of these braided monoidal categories, you have to first to relax the symmetry condition. You have to consider general morphism and not only isomorphisms. Otherwise, everything collapses to a braided monoidal structure, and you have to consider more tensor product operations. So this is one thing.
Because of this homotopy equivalence of spaces between Dn and the classifying space, I should still think of these things that you've relaxed as holding up to homotopy?
No. It's what do you mean by the thing which? No, you still have also some constraints, so it's really a rigid construction. I mean.
Mm-hmm.
So the main fact is this. So you see. So yeah, in that case, I'm considering. In this case, I'm considering classifying spaces of group weights.
Yeah.
So in that case, you consider classifying spaces of group weights. So you get Allenberg-MacLane spaces. In that case, you have no more group weights. So this classifying space is not fibrant. It doesn't satisfy the Kahn condition. So this means that if you compute the homotopy of this object, it doesn't reduce it to a fundamental group. You have more. Okay, so this is really crucial. So it's not ISO. Not necessarily ISO. Okay, you need this condition to I mean, otherwise, if you don't, you relax in the sense that you consider morphism instead of isomorphisms. Okay, and this weakening implies that if you take the classifying space, you don't get an Allenberg-MacLane space. Okay, you have spaces which have homotopy in whole dimensions. Okay. So this opera is not good enough for me. I need a coferent, something which is a coferent resolution. So I'm not going to, probably not going to say match. I would like to mention that you can define this opera. I would like to say that you have such a nice coferent replacement.
If you take a fiber replacement in topological operas or in categorical operas?
Yeah.
Which one?
So sorry?
You can take its cofibrant resolution of categorical operas or topological operas. Which one you take?
No, I need a coferent replacement in topological operas.
Topological.
Yeah. And that what I can do in that case, so I'm not just going to mention that such a nice coferent replacement is provided by Batanins n of rods Hn. So from this upright you can form. So this one is related to coferent resolution. That's what I need actually for my purpose, is to associated simplisher upright. So from this upright you can get number of rods, small h, which is a usual upright in categories, and then take the classifying space of this upright in categories, and this one. So maybe I can just briefly say. So it's an upright in the category of categories. say that so the object of this subprod is again a Frere prod generated by planar trees with n levels. So for instance, this is a planar tree with 2 levels. So this subprod is a covariant replacement. This means that you have a map from this subprod in topological spaces to the classifying space of Mn. And this map takes this object, so if I remember well, to tensor 1, and this one to tensor 2. So with this object, I can get some kind of, so I'm not going to describe the morphism, so it's some kind of generalization of a process for PAB. Okay. And so with this object, I get some kind of nice combinatorial model of covariant operads which I need for the performance of homotopy computations. Okay. So just last remarks. So this operad Hn is related to, in some sense, encodes a subspace decomposition of Ketzler-Jones, Fulton-McPherson operad. So this is an operad in topological space obtained by some kind of compactifications of a configuration space of R points. Okay. And this operad is also, so this Fulton-McPherson operad is also covariant as an operad in topological space. Okay. So I've said what I wanted to say about operads. Now the infinitesimal Bride operads. Okay. So I will start with the facts about the cohomology of little disk. So if I want to compute the cohomology of a little 2D space, so I can consider the space of, so I can reduce, so this is the space of configurations of R little disk, so for a fixed unit disk. And if you want to compute the cohomology, you can forget about the radius and consider the space of configuration of points in the disk. Okay, then. Space of configurations of R points in the N. The cohomology of this space is well known. So it's a free-graded commutative algebra with generators Wij of degree n-1. So generators associated to each pair ij divided out, quotiented by the Arnold relation. The ideal generated by the Arnold relation. So the Arnold relation explicitly reads Wij times Wjk plus Wjk Wki plus Wki Wij is 0. Okay, so this is for every triple ijk. And so In that case, I take. So I have to extend this Wij to pairs with a converse order. And I assume that the symbols are even or odd depending on the parity of n. Okay. I think they are even if n is even, odd if n is odd. Okay, I think that's -1 to n Wj. Okay. So the fact is that this upright is causul. You have this first statement. Second statement, this upright is causul. This algebra, sorry. So I call this algebra A. The dual of the form like that. So the dual of this algebra is the enveloping algebra of some Lie algebra. And this is Lie algebra, which will define my n-dimensional version of a Lie algebra of infinitesimal brights. So this K R. This is the free Lie algebra with generators in degree n-1. Okay, generators associated to each pair ij, and divided out by the infinitesimal bright relations. So quotiented by the infinitesimal bright relations. So we call these relations. We have two relations. Relations says that Tij, Tkl is 0 if Ij, Kl are all distinct. And you have also the Young-Baxter relation. And again, I set Tij to be -1 to n of Tja if I is larger than j. So this algebra is causul. This implies that if I take the Chevalier-Allenberg cochain complex on this Lie algebra, it's some kind of covariant model of a comergy of Dn. So this means this is a quasi-iso of commutative algebras. So the comergy, it's a quasi algebra which I regard.
No, in the infinitesimal bright relation, it's Tk plus Tkj or Jk.
I think it's Tkj. So no.
I don't know. I mean,
I don't remember.
it doesn't matter, but
yeah. Okay. Yeah, I don't remember. So.
Okay.
Okay. Sorry. So, to be all.
You mean that all the...
You can check. So just compute, so it's an exercise. So Bruno has given a course about the causul duality of algebras. Just compute the causul dual of this algebra, and you will see if this is Tkj or Tkj, okay?
And all the indices are different.
Yeah,
You want to
exactly.
say.
Yeah, exactly.
Not exactly what you've written.
No. So I'm considering the transitive closure of this relation, okay? Otherwise, I would put parentheses. Okay.
I can get Pn of so Ij.
Sorry, yeah.
From
This is
one
from one between, this is a pair in one.
Okay.
All right. So this is a quasi-ISO of DG commutative algebra. I mean, this is the kind of things that I will need to do homotopy computation. So in the case of DG commutative algebra. So this object also is quasi-free. Okay, this means cofibrillant in DG com. And so now you have the following basic observation. So this collection of P and R of free algebras in R inherits some kind of infinitesimal or additive that you prefer. I prefer to say additive or periodic composition operations. Giving a counterpart on this object of the operation yielded by the operator structure of the Dn. Oops, this is the code chain complex. Composition of our operations induced by the operator structure of Dn in cohomology. So in the map here, this cosult relative equivalence preserves, so commutes, so giving counterpart means that precisely means that this object is a coprod in commutative algebra, so it's the dual structure of an operad, which is equivalent to this object as a coprod in DG commutative algebra. Okay, so in some sense, so what you have to retain is that this commutative algebras give a good model of this cohomology coprod. This gives a good model of the cohomology of the little disk together with the coprod structure. And we can do computation with that. So we can do computation with that means that I can go back to spaces. So I have the Sullivan functor. So and the adjoint of the Sullivan functor, you have a functor G dot from DG commutative algebras to simplicial sets, which you can prolong to topological spaces by using generalization. It takes a DG commutative algebra to the simplicial set given by the collection of DG commutative algebra morphisms from A to something which I will denote by omega upper star of delta dot. So this are the DG algebras of piecewise linear forms or Durham forms or semi-algebraic forms or any kind of form that you like on the simplices. So this is the functor classically used in Sullivan's rational homotopy theory to associate a space to a DG commutative algebra. So you can prolong this space to operate. In my case, what I need to take, so it's a derived functor. And to define this derived functor, I have to take a covariant replacement of this cohomology algebra. And this covariant replacement can be provided by this construction. So You can take that as a definition. So this gives an upright in space. Okay. So it's in some sense it's the upright in spaces which is determined that the structure which is retained at the level of a cohomology. Maybe I should be more precise. So this gives an upright in spaces. Spaces determined in the cohomology of D2. Dn. So you start with Dn, the upright in topological spaces. You take the cohomology. So in principle, you forget some structure, you lose some structure, and you go back to spaces by using this construction. So now for part, in concluding part, so probably don't have much time to enter into details. My goal, so the main objective, so the problem, rather, because I'm not able to sort out this problem completely. So to determine several things. So first, some H hot. I'm not going to explain what it is. It's some kind of homotopy version of upright automorphisms. An H iso of Dn from this Lg so this is an object which acts on this isomorphism set. Okay, so it reflects some kind of internal symmetries of this upright in topological spaces. Okay, and this I will focus on this space. So this is the space of maps. So Dn, I will forget the Dn. Yeah, okay. Shoot. So this is the space of maps, of upright maps, from Dn to this upright in spaces. Which are the identity in cohomology. I forget to say that the cohomology of this upright, so this construction is idempotent in some sense. If you take the cohomology again, then you retrieve the cohomology of Dn. Because Dn are small and nilpotent enough.
And what is Dn hat there?
Yeah, Dn hat means a rationalization. Okay. Maybe, okay.
Okay.
Okay, so here there are self maps of Dn which are rational homotopy equivalencies. Okay. These are okay. So the okay. I'd like to focus on this object. So it's a topological space, or simplicial set. And the connected components of this space, you actually get this space of iso in the homotopy form. But to have a space is better than to have just a set of homotopy classes. Okay. So first fact, so it's a main theorem. So it has been established by So peoples, in the case n equals 2, this is a form of Dimitri-Tamarkin using Drinfeld's associators. And this is valid for in the case of a Q, the rational coefficient case. For n larger or equal to 2, this is resolved by Consevich. This is just in the case where K is the round field. And this theorem says that this space is not empty. So this says that if you take this construction, so this means that you have a weak equivalence actually connected this upright. So yeah, I cannot take Dn, I have to take a cofactor replacement. If you take the cohomology and go back, then you get an object which is still weak equivalent to rationalization of En. This means that you don't lose rational information if you perform the cohomology construction. So this statement, the code is a kind of formality also. Okay, the conjecture is that this is still true for the case K, where K is Q. Okay, so just now I can explain the connection with associators. Okay, so I have the map like that to conclude this talk. I have a natural map that way, which goes that way, because to each associator, actually I forgot to explain something. So CD hat, you can identify this. It's really the same as if you take this in the case where the cohomology, in the case n equals 2, then you get this CD hat, or sorry, the classifying space of CD hat. So if you take the standard Drinfeld-Connolly algebra, which is ungraded, and if perform that derived functor construction with this cofactor resolution, then you get the classifying space of the chord diagram apparatus, so it can be identified algebraically. Okay. And each associator, which is basically which corresponds to an iso from PAB to CD hat, gives rise to a weak equivalence from E2 to this object, to this space. Because this is the same as, so this E2 you can take the cofactor replacement of this upright. So that way you have a map that corresponds from this side to this side. And the theorem is that this correspondence is 1 to 1. Okay, which means that if you take this space, then you have the pi 0 is in 1 to 1 correspondence with this object. You have no higher homotopy. So we say that you can take this space for n larger than 2 as a higher dimensional version of the torsor of Drinfeld associator, which is just this object, I remind you. And just to say a few things, so the way to prove this statement is to use some kind of deformation complex spectral sequence using a toward decomposition of this object on the right hand side. And you see that the equation, so in that case, what you really see that the equations of Drinfeld associators really show up in the spectral sequence associated to this tower of vibrations. I mean, the hexagon condition corresponds to some kind of equivalence constraints, and the pentagon equation corresponds to a differential term in the spectral sequence. And what you get is that so I'm not going to explain this computation. So the idea is to use a spectral sequence converging to this homotopy. And you can check that E1, E2, sorry, is you get exactly the equation of the equation of associators, E2. So that's the main point. So and to get this result, you use that the operator D2 is Kosul as an operator. So I've already used that D2, the cohomology of D2 are Kosul as algebras, and I'm also using that D2 is Kosul as an operator. Okay? And so you can form the same spectral sequence in the higher dimensional cases, but so it's the same spectral sequence. You get more or less the same components, except that they are distributed differently. I mean, you have more in higher degrees. I don't know yet how how to identify all cycles in the spectral sequence. Okay, but what I conjecture still is that the spectral sequence, so in that case it degenerates at E2, and I still conjecture that the same similar degeneration phenomena holds for the higher EN operands. So thank you very much for your attention.
Question?
Can you give a hint why this case of high n is different, right? Because like for n equal 2, as far as I recall, basically say the Drinfeld's proof why one can do it over Q is by linearizing the problem,
exactly.
right? You have, roughly speaking, only equation, you can replace it with an equivalent linear equation.
Because you work on this side, which is an algebraic object, and you use that. Basically, what you use it's a pro-unipotent torsor under a pro-unipotent group. Okay, and to get the higher cases, what you have to prove that. So in that case, the difficulty that you see, you get so what the pro-unipotent group would be. The pro-unipotent group would be this object. Okay, but basically you have to consider. So it's not a group; it's a collection of spaces. You have to consider the homotopy, the pi naught. And there the pi naught 2. Okay. So you have to, in order to get the result, you need some kind of qualitative statement asserting that the group of self-homotopy classes of an Euclidean spaces is a pro-unipotent group over Q. Okay. It should be some kind of general. So it's something which is classical for spaces, which is proved in Sullivan's paper about rational homotopy. If you take those rational self-homotopy equivalences of a space satisfying some infiniteness condition, then you get a unipotent group. To prove this statement, Sullivan uses a minimal model theory. Okay, so a different approach has to be set up to get such qualitative statement. But the point is that as soon as you prove that such structure results all, I mean, if you can prove that this object by another method is unipotent, and so on, which I think should be the case, then you get from the rational case, from the real case, you get the rational case of a formality result. But it's not yet clear, obviously.
Okay. Any other questions?
Yes, I have a question about the early part of your talk, where you referred to the existence of an R matrix satisfying the extra equations. I like that because it gave some specificity, some constraint down there.
Yeah.
But did it play an essential role subsequently?
No. Just to give an intuition of this operator CD. So to explain what an operator is, you explain which kind of algebras this operator encodes. I mean, operators are somehow some kind of universal operation as stated.
So it was an example rather than a constraint.
Yeah, so for PAB are universal operations acting on very modular categories, and CD are some kind of universal operations acting on the representations of Lie algebras that could be such
Yes, so I have one question. So this is a higher associators, right?
Yeah.
Usual associator,
So
we have a nice description. The set of formal power series
Exactly.
with pentagon, hexagon
Exactly.
equation.
But what is missing in that case? So,
Yeah,
so
yeah.
the point that you have this nice description in terms of so in that case you really see this description showing up. I mean, if you check what is the E2 in degree 0, then you get exactly Lie power series in P3. I mean, Lie power series on T1, 2 and T2, 3, and the equations.
You have also algebraic
Yeah,
present.
but the point is this. So but the object is much bigger. I mean, and so it's not. So this in this case, you get you get not only P3 but all PRs because of the brain. You get many things in degree 0. Right? So it's more complicated to get.
Any other question? Okay, thanks for speakers.